Hello, hi. So this is a continuation of chapter 4 of the textbook, in which we cover linear programming and we do a lot of modeling examples. So we have done several modeling examples such as the diet, the diet modelings, the transportation examples, and a few others. So we are left with three more examples, where the first one is the blend example, and then we have the multi-period scheduling system, and the last one is the data envelopment analysis. So this is a recorded a lecture, because if you remember last time, just before the semester break, we had a holiday on Monday. Alright, so let us just continue with this one. And I'm referring to the textbook here because the textbook has more information than what we have in the slides. So if you look at the textbook that is being given to you on page 133 to understand this problem better, we have a petroleum company which produces three grades of motor oil. So we have super premium and extra, and each of this motor oil is made of three components. So we have component 1, component 2, and component 3. So the company wants to determine the optimal mix of the three components in each grade of motor oil that will maximize the profits, and the maximum quantities available of each component and the cost per barrel are given in the next slides. So you can see in the top table, this is the cost of each of the components. Like for example, you have three different motor oils here. You have super, you have premium, and you have extra. To make super, you need to mix all these components, component 1, 2, 3, and then the same components 1 to 3 is also being used to make premium oil and extra oil, but the composition will be different. So let's look at each of these components. So the first component, the cost per barrel is $12. Okay, and the second component is the cheapest one, $10, and the most expensive one is the component number 3. And the maximum availability of component 1 is 4,500 barrels, and this is the availability of the maximum number of barrels for each of the other components. So to ensure the appropriate blend, each grade has certain general specifications. So this is where it is different, between super, premium, and extra, even though they are made of the same three components. So for super, you need to have at least 50% from component 1. Okay, so which means that to make like this is 1 barrel, let's say this is 1 barrel of super. So at least 50%, half of this must be from component 1, and then it says that not more than 30% must be from component 2. So component 2 maximum is 30%, but minimum for component 1 is 50%. This is for super. And these are specifications for premium, where at least 40% is from component 1 and not more than a quarter must be from component 3. And then for extra, you need to have at least 60% of component 1 and at least 10% of component 2. Alright, so the selling price per barrel for super is the most expensive, $23 per barrel, and you have $20 for premium and $18 for extra. So let's look at other information. So what we want to do here is we want to determine what will be the optimal mix of the three components in each of the grade motor oil that will maximize the profits. So we are talking about the profits here, but if you can see from the previous slides, what we have is we have the cost and we have the sell price. So to get the profit, we have to subtract the cost from the selling price. Now let's look at the next sentence. The company wants to produce at least 3,000 barrels of each grade of motor oil, which means that you want to produce at least 3,000 barrels of super, 3,000 barrels of extra, and 3,000 barrels of premium. Now, the first thing is we know now that the objective functions is to maximize the profits. and the profits can be obtained by taking into information taking into account the cost and also the selling price. And now the next thing that we should do is to determine what would be the decision variable. So here we have three components, and these three components need to be mixed into three different products. So we can say that we have 9 decision variable. So the decision variable can be represented by X, I, and J, where I is component 1, component 2, and component 3, and J is super, premium, and extra. So for example, if you have like 1S, okay, so this means that this is the compositions of component 1 to make super oil. So if you have like 3P, so this is the component 3 which is used to mix for premium oil. Okay, so in total you're going to have 9. So 3 times 3 is 9. Now let's look at this. Okay, I don't want to jump into that one first. Right, so if I can I'll use paint. It's easy for me to draw. Okay, so imagine we have like 3 barrels here. So here we have super, and this one we have premium, and this one is we have extra. Okay, so for each of these we have a mix of elements 1 to 3, 1 to 3, and component 1 to 3. Alright, so if we have a decision variables of X, oh, it's gone haywire. Okay, I'm so sorry. I wish that it could be better. Let's just forget this. I go back to this one. Alright. Okay, so now let us look at what are the constraints that will be involved in this problems here. We go back to the questions here. So let us start with I'm gonna start with this one. It doesn't matter where do you want to start here, but I want to start with this one because I'm following the textbook. So this is the first constraint. The company wants to produce at least 3,000 barrels of each grade of motor oil. So it means that this one, whatever it is, like if you have super, so you need to have super more than 3,000 barrels. So super is made of component 1, okay, 1S plus component 2S plus component 3S. So this equation should be more than 3,000. So similar to extra, so you have 1E plus 2E plus 3E, and this must be more than 3,000. And finally you have premium, okay, 2P and 3P must be larger or equal to 3,000. Now some of you may ask, how sure are you that we are going to use all the 3 components for each of this motor oil, yeah, for super, extra, and premium? Now if we look at this, we know definitely that super must have component 1 and it must have component okay, for this one we are not really sure, yeah, because it says that no more than 30% of component 2. It could be that we don't use component 2 at all for super. It could be, alright, because we can have component 2 but shouldn't be no more than 30%. But it could be like in the end when you get like 2S could be 0. It could be, because there's no restriction. It doesn't say that it needs to have a component 2 in super. Alright, so how about component 3? Component 3 is denoted by 3S because it is not being explicit in the specification. So it could be that the component 3 will be used to make up super, or it wouldn't be used. We don't know, okay, because the specification is not given. But what we know is that if it is 0, never mind, you just put it into the equations. But basically what we want here is that all the super, all the S here, the combinations of all the components that make up the super oil must be larger or equal to 3000 barrels. So we have already satisfied this requirement. Yeah. So now let's look at this one. So this is the maximum availability of component number one. So the component number one, 1s plus 1 that is used for E plus 1 that is used for P must be less than or equal to 4500. And then we have 2s plus 2E plus 2P, and this one must be less than 2700. And the same thing for the third component. As you can see in the first equation, we have all the ones, yeah, because we are talking about the component number one, and the second equation we are talking about component number two. So we have already satisfied this constraint, which is this is the maximum availability of each of the components. Now the next constraint consists of this component specification. Now we want to look at each of this. So the first one, to make super, it needs to have at least 50% of component 1. So imagine this is a barrel of super, at least 50%. It could be more, but at least, yeah, the minimum that you need to have is 50% must be from component 1. So with this being said, you can say that the ratio of 1s, okay, so to make s, the ratio of 1s out of the total, because you know the whole composition might be from component 1, component 2 and component 3. So we are only talking about s here. You can see that all the variable that we have is referring to S only, because this is, we are talking about the motor grade super. So the ratio of component 1 to the mix of all the components, okay, must be more or equal to 0.5. Okay, must be more or equal to 0.5. And again, we want to make it linear, so we want to put all the variables on the left hand side and all the numbers on the we don't want to have like a ratio like this, so we can rearrange it so that x1s is larger than or equal to 0.5 x1s, okay, plus 0.5 x2s. I really wish I can use paint right now, and this is 0.5 x3s. Alright, and then we want to rearrange it to be on the left hand side. So here we have, because this is 1 minus 0.5 is 0.5, so you have 0.5 x1s and minus 0.5 x2s, okay, and then you have let me see, minus 0.5 x3s, and then this is less than or equal to 0. Okay, alright, so that is for the first component specification. Now let me do another one example using the second specifications, and for this one I need to clear everything. Okay, we are focusing on this one. Okay, not more than 30% from component 2. So we are still talking about super. So here, component 2 of super, out of the total mix, which is 1s plus 2s plus 3s, okay, must be less than or equal to 0.3. So for this one, we just put 2s on the left hand side, so this is less than 0.3 times 1s plus x2s, this is x3s, okay, plus x3s. And then we want to bring all the variables on the left hand side, so this is like 1 minus 0.3, so we have 0.7, so 0.7 x2s minus 0.3 x1s minus 0.3 x 3s must be or less or equal to 0. Okay, but in order for us to insert this data into Excel, so usually we start with 1s first. So you start with negative 0.3 x1s plus 0.7 x2s minus 0.3 x3s less than or equal to 0. Okay, I really wish I have a more functional pen and you know uh, a better way of writing this by hand. So you can do the same for premium, the component specifications for premium and also for extra, and the full details of the calculations is also given in the textbook. So basically, how many constraints do we have? Okay, so I haven't talked about the objective function yet. So the first constraint is the maximum availability of each of the component, where this is for component 1, component 2, component 3. And then we have the 6 component specifications. Okay, 1, 2, 3, 4, 5, 6. And then we also have, like, this is the number of barrels of each of the motor oils that we have to produce, which is at least 3000 barrels per motor oil. Okay, so this is another 3. Now let us talk about the objective function. So the objective function is the profits. Yeah, so Z is the profit, and we get this profit from the selling price minus the cost per barrel. So there are 3 selling price and there are 3 cost. Yeah, but because we have 9 variables, so basically what does it mean is something like this. So this is like component 1, component 2, component 3, and if I can remember, let me see, the cost of component 1 is $12. Okay, so I put there 12, and this is 10, and this is 14, and this is super, and this is premium and extra, and the selling price for super is 23, this one is 20, this one is 18. So what we want inside these 9 cells, yeah, is actually the profit. So the profit is taken by the selling price minus the cost. So the first one is 23 minus 12 is, we have 11. Okay, and then 23 minus 10 is 13, and then 23 minus 14 is 9, and here you have 8 and 10 and 6, and you have 6, 8 and 4. Okay, so basically this is the cost for x1s. Okay, so it's 11 x1s plus 13 x2s and etc. So in total you have 9. So we have like 9 decision variable. We have this as the objective functions, and we have already established a long list of constraints. Now we want to try to solve this using Microsoft Excel. So for this I have actually given you the Excel file which I have uploaded on Spectrum. So it looks like this. Alright, so here is the component I in grade J. So basically these 3 will tell you how much of the component 1 to 3 that will be used in super, and the next 3 will tell you how many of the component 1 to 3 that will be used in premium and etc. And here on the column C we have the profits. We need this information in order for us to achieve the maximum profit. And this maximum profit, the formula is the sum product of column B multiplied with column C. So whatever it is, whatever amount that you have on each of these x1s until x3e, you multiply with the profit. So we put all the constraint on column H basically. Okay, and for this one each of the formula will be different depending on how you actually write the equation. Now let's look at the first one. So this is component 1 availability. Okay, so the availability of component 1 is given by this one. So you look at where I highlighted the cells, so it is B7, which is the blue one here. B7 is X1S, X1P, X1E. So now we are only talking in terms of X1. Okay, X1, S, P, and E. Alright, so this is all the component 1 that is being used in super, premium, and etc. and extra. And the constraint is that it must be less than whatever is available, which is 4,500. And now we look at the component 2. Alright, is X2S, X2P, and X2E. So basically this is the component 2 that is used in super, premium, and extra. And same goes to the third one. Okay, so I believe the next one is talking about the equations that we talked just now. So this one you have to really follow the equations. Now let me go back to the equation. Is this one. So you have 0.5 x1s minus 0.5 x2s minus 0.5 x3s. Okay, so try to remember this, and we go to our Excel. So it's this one. Okay, so it's 0.5, all right, x1s minus 0.5 x2s minus 0.5 x3s. For this one you cannot copy down because each of these will be different. Yeah, so like this one, it is following the next equation, so you just follow suit. If it is talk about x1s, then it should be here. If it's x3p, then it should be on cell B12. Yeah, okay, so you just follow suit whatever equations is being that you have derived just now. And the last three. All right, so the last three is the compositions of all the supers. You see it's highlighted all the x1s, x2s, x3s, all the component that make up super. Okay, and super must be larger, or must be at least 3,000 barrel. And this is the next one is on the premium. So we have x1p, x2p, and x3p, and the last one is on the extra. Okay, so whatever it is, the equations or the formula that you should put on cell H, this must follow whatever it is that you derive in this one. Okay, so if you're not sure, you just go back and look at the equations. Okay, and this is the signs of the constraints. Again, you have to look at the constraint, and also this one, what is the number on the right hand side of the constraint. Okay, now let us try to solve these problems using solver. Okay, so we set the objective, which is the total profit here, and we set it to maximum by changing the variable here, okay, on column B, which is the solution. And then okay, I just want to change everything else. This one is simplex. Alright, this is the non-negativity. Now I want to add. We want to add one by one. Okay, first is okay, because this one is less than, so we can put them together, so it's like less than. All right, and then I want to add, oh, there are three of them. Okay, I should have add them together. Add. Okay, and this one, because the sign is different, so this one is larger than, you have to be careful with the sign. Okay, and then I want to add again, and this is less than this one. All right, add, this is larger than. Okay, H11, so this should be J11. All right, and this is less than H12, so J12. And then we have the rest of them because they have the same sign, which is larger than, so I can put them together, larger than, and this one. Okay, then I just click OK. Just want to make sure that everything is correct. Less than H10, J10. Okay, and H9 J9 H10. I hope I'm doing everything correct. Okay. H9 H9. Okay. I really hope I did everything correct. Let me just try to solve this first, yeah. Okay. I think it would be somewhere haywire. Select surplus. Must be okay. So this is something wrong. The first instinct that I get is like this one. The constraint achievement is negative, and this should be like this one is very problematic, because this is like this negative is larger than or equal to 0, so it shouldn't be, because we want whatever number here is actually that larger than 0. So let me just run one more time, yeah, because it is quite long here, so I just want to reset all, and let's do this again. So I set the objective, which is this one, by changing whatever here, okay, B7 to B15, and then I want to add, okay, the first one is H6 to H8, alright, and this is less than J6 to J8, alright, and then the second one is H10, alright, and this one must be less than J10. Okay, and add H9. I'm following the textbook here, but I'll see why they do this. It says here that H9 is exactly equal to J9. We're going to test on this later. I try to understand this, but we just follow so far. And H11 is larger than J11, alright, and then H13 to H17 is larger than J13 to J17, and the last one is H12. Okay, and this is lesser than J12. Alright, this one I follow the textbook one by one. Let me check. H10, J10, H6, okay, and H11, J11, H12 less than J12. And this is something that I didn't expect, the equal sign, but whatever it is, just try to solve this. Okay, all right, so let me just find an explanation on why I got the correct answer as in the textbook here, but I try to understand why this is set to be equal, H9 equal to J9. Now let me see, H9 is this one, so the blend super, okay, so this one must be, it says there that this is like equal to, and this is like this one, okay, where it's 0.5 x1s minus 0.5, it's this equation. Let me just show you this one. It's the very first, this one, 0.5 x1s minus 0.5 x2s minus 0.5 x3s, and the sign we have is actually larger than, but the sign that is being used in the textbook is actually equal to. So let me just try to change this. Yeah, try to change this to larger than, as we agree on the you know on the that thing. So I try to solve. Okay, let me check the answer whether it is exactly the same. I think it is. Yeah, it is the same. So there might be some errors in the textbook, but we are happy to get the exactly the same results. Now let us interpret what does it mean. Yeah, so you can't interpret from here. Basically, you can just look at this in terms of whether it actually satisfy all the requirements and all the restrictions. But the most important part is this one. So this one, component 1 that is being used to make super is 1500 barrels of component 1 and 600 barrels of component 2 and 900 barrels of component 3 is used to make up component 1. Now let us see this one. If I put the sum of all this, okay, it must be 3000, and it does satisfy. It is actually this one. It does satisfy the requirement to produce at least 3000 of super. Now the items that make up premium is this one, and we are able to come up with 3000 barrels of premium. And the last one is, I believe, is the same. Yeah, it's also 3000. Basically it's this one, because this is the sum of those three cells. All right, so basically we are able to satisfy all the requirements. Specifically, we are able to produce 3000 barrels for each of the motor oil. At the same time, we are using all of component 1 and all of component 2, but we have some surplus on component number 3, where we only use 1800 barrels of component 3, while the availability is 3500 barrels, so we have a surplus of 1700 barrels. For the others, it's quite difficult here, because in in terms of the equations, is it has been rearranged, so we can't really say much about this. Okay, but basically what we can say is that this is the maximum profit that we can get, that also satisfy all of the requirements that we have set before. Okay, so these are all the requirements. It's hang. Yeah. Okay. Right. Now let us go to the next example on the multi-period scheduling example. So in this example, we are using PM computers. Yeah, this, I believe this is a supplier. They have their own brand of personal computers, and all right. So I'm reading this. It says that the PM sells most of its computers locally to different departments at state universities, as well to individuals and business in the immediate geographic region. And PM has enough regular production capacity to produce 160 computers per week. So they not only sell computers, but they also produce computers. Yeah, and the production capacity is 160 computers per week. However, it can produce an additional 50 computers with overtime. That being said, if you're working at the normal capacity, this company can produce 160, but if there is a huge demand, then they will be able to produce an extra 50 with extra cost. So the cost of assembling, inspecting and packaging a computer during regular time, in order for you to produce the 160 computers in the normal capacity, the cost is 190. However, if you need to produce an overtime production, yeah, it costs $260. And furthermore, there's another cost involved here. it costs $10 per computer per week to hold a computer in inventory for future delivery. So basically what it means here is that if the demand per week is 160, then it's just nice because this supplier, they can produce 160 computers per week. However, if the demand is higher than 160, then um, they need to take the overtime workers, for example, and they need to pay more for the cost of producing at the overtime capacity. However, if let's say they produce more than what is demanded, like if they produce 160 but demand is only 100, then they have to pay $10 per computer for inventory cost. Okay, so the ideal is that we want to produce exactly, as the amount demanded. Now let's look at this. This is the order schedule that I have received. So they make an order schedule for the next 6 weeks. So in the first week, they would estimate that there will be 105 orders for computer. And then in the second week, so okay, now let's look at this one by one. Yeah. So during the first week, the order is 105. Well, this company can produce 160 computers per week. So the question is, do you want to produce 160 in the first week, or do you want to produce 105? If you produce 105, then whatever that you produce will be sold in the same week. So you don't have to pay for the inventory. However, as we go to the second week, because the regular capacity is 160 and the demand is 170, so for the 10 extra that you need to fulfill the demand, you need to pay more for the cost. So might as well that you produce a little bit more on the first week, and you just pay for like $10 per computer, and you keep it for 1 week, and then you can meet the demand in the second week. And if you look at the third week the demand is quite high, 230. Okay, so same goes for fourth week, which is the number of orders is actually exceeding the regular capacity. But as we go through week 5, it is a little bit less, but week 6 we have a very very high demand. So the question is that how many are we going to produce each week in order for us to, of course, we want to minimize the cost. Yeah. So is it better for us to produce a lot and then we pay for the inventory cost, or is it better for us to, use the overtime cost whenever the demand is not met? Now let's try to solve this problem. So the decision variable that we have is we have Rj, okay, where R is the regular production. So we have Rj is from R1, R2, R3, R4, R5, and R6. So if you put R1 as 160, that means that you are going to produce 160 computers at the regular capacity. Okay, and then OJ is the overtime production of computer. So let's say the demand is very high, 160 is not enough, and you need to add more. So this is where you put the OJ. Okay, you use the overtime production, and of course the cost is actually higher. And then finally you have the IJ. So this is the inventory cost. So let's say during the first week the demand is only 105, but you produce 160. So how about the 55 computers that are not being sold in the first week? So you need to keep it for 1 week, and it will incur the inventory cost. Okay, so now we have 6 plus 6 plus 5 decision variable. So in total we have 17 decision variables. And why does it only have like 1 to 5? Because I believe somewhere, okay, somewhere in this text or somewhere in the textbook, it says that in the final week which is on week 6, we don't want to have anything leftovers. So we want to meet all the demands and we don't want to have any computers left over. So we just want to, like Malaysian, we call it like ngam ngam, you know, at the end of the 6th week, there's no leftovers of computers. So that's why we want to set I6 as 0, so we only have like I5. Okay, now the objective functions is written in this way. So each of the Ri, okay, each of the Rj, where j is equal to 1, 2, 3, 4, 5, and 6. Okay, it is associated with the cost of 190. So this is 190 for R1, 190 for R2. So R1 is the regular production at week 1, and R2 is the regular production at week 2, and so on. And the cost associated with the overtime capacity or the overtime production is 260, and the cost involved in inventory is $10. Okay, so what are the constraints that we have? Right, now let's look at this one. So Rj, the regular capacity, must be any numbers below than 160, because the regular capacity is only up to 160. You cannot produce more than 160 under regular production. So if you need more, then it should be under overtime. Okay, but here the overtime is set to be, I believe it is being mentioned somewhere in the text. Yeah, the available overtime production capacity of 50 computers per week also results in, I think this is not 150, this is 50. Okay, so there's the typing error in here, because it is being said in the, yeah, it's this one. If you know, on regular production 160, but if you need overtime, it's like 50 computers, 50 more computers can be produced with overtime, not 160. So there's typo there. Right, so now let's look at the first week. So we look at the constraint is being sorted by weekly basis from week 1 until week 6. So in the first week, whatever that you decide to be on the regular plus whatever that you decide to be on overtime plus the inventory should be exactly 105. Okay, so here what it means is that, for example, I take this lah. Let's say in the first week, the regular production, you want to produce 100, let's say you want to produce 160, because you know that the coming week the demand is going to be higher, so you want to produce 160. Okay, and plus overtime, you don't think that you need any overtime, never mind, you think that 160 is enough, and then you need to minus 55, and this 55 you need to bring it to next week, yeah, in order for you to get 105. All right, so this is one thing. So next week, let's say R2, you want to still produce 160, and maybe still no overtime, this is just my guess, yeah, still no overtime, but you add whatever that you have from the last week. Okay, that you take it from the store, you have 55, and then you minus with something and you have 170. So this is the amount that you need to store. So 160 plus 55 is 215. 215 minus this one, so here, if I'm not mistaken, is 45. So this 45 you carry forward. Okay, so I really hope you understand this, yeah. So let me re-explain this using Microsoft Excel. This one is also given on your spectrum. So let's say this one I just type in. Let's say in the first week you want to produce 160, no product, no overtime. Okay, and then the demand is 105. I want to put the demand as yellow in here, so you know, or red lah. Okay, so this is the demand and this is the inventory. Inventory, I put it in green. Okay, so that's this is right. So you produce 160 under regular production, you don't produce overtime. So because the demand is 105, so you carry forward 55 computers to the next what to the next week. Yeah, so in the second week, let's say you want to produce 160, and let's say it's still zero overtime, and then because the demand is 170 over here, so you have an inventory of 45. And let's say you want to, you know, produce 160 and then zero what zero overtime, but here there's a problem because the computer available is 205 while the demand is 230, so we need to meet the demand. So for this one, we don't have, we need to have 25 more. Okay, 25 more. So on the third week, you decide to have an overtime production, but instead of doing this one by one like this, so why don't we try to use solver? So I'm going to delete all this, and I'll try to use solver. So I go to data, I go to solver, and I want to reset everything. Okay, so setting the objective is this total cost, yeah, which is C13, and we want to minimize by changing the variable in the column B, okay, which is the regular production as well as the overtime production. So these are the figures that we want to change. So what are the constraints? So the first one is, okay, oops, no. So whatever that we have here, whatever is the regular production, must be less than or equal to 160, because we cannot produce more than 160 under the regular production. Second is the overtime production, alright, must be less than or equal to 50, not 150, yeah? 50. And the third one is the number of computers available here must meet the demand, must be higher or equal to the computer orders. And we just click OK. And make sure that everything else is correct. I'm using Simplex LP, and I solve, and done. Okay, so let's see if we really meet all the demands. We look at here, okay, it seems like all the availability is exceeding all the orders, which is good, okay. And in the final week, this is very, very important. In the final week, the number of computers available is exactly the same as the number ordered, and we left with no leftover, okay, which is very good, which is what we want. And then, so if, like, let's say your supervisor asks you to come up with this scheduling system, and then you tell your supervisor that, okay, each week we still have to produce at regular production 160, because even though the demand fluctuates, yeah, sometimes it's way lower than 160, but you know, in order for you to meet all the demands in the future, you need to produce 160. Starting from the third week, you may need to produce an overtime production. There will be inventory costs involved, but eventually this all leads to the lowest total cost. Okay. All right. And now let's go to the last one, which is the data envelopment analysis. And this one is the most unique applications of linear programming compared to all the other modelings that we have done in the past. So basically the DEA, this is an application that compares a number of service units of the same type. So we can do this on universities, on schools, on restaurants, and etc. So basically what we do is that we compare between the inputs or resources and the outputs. So we believe that those schools or those restaurants that have better inputs would have a higher output as well. Like for example here, if we want to compare universities, let's say we take certain characteristics here. So if we want to compare University Malaya and we want to compare some other universities like UKM, USM and UPM for example, or we can also take private universities. So what are the inputs of each of these universities? Maybe the funding, maybe the number of lecturers, the number of professors, the number of students. These are all the inputs, yeah. Like for example, if we have more compositions of professors, then we would expect that this university would perform better in terms of research. And in this example, we are using schools, yeah. So we believe that these schools, um, the inputs, um, we are comparing between school A, B, C, and D, yeah? Elton, Biggs, Carey, and Delancey. So the state has implemented a series of standards of learning tests in reading, math, and history that all schools are required to administer to all students in the 5th grade. So the average test scores are a measurable output of the school performance. So the output that we measure here is in terms of the scores in reading, math, and history. And in terms of the inputs, we have the first input is the teacher to student ratio. So the higher the teacher to student ratio, the better we would expect the scores will be, because teachers have lesser students and they can actually pay more attention to each of their students. And the second input is the supplementary funds per students. Of course, we would expect that if the funds for students is higher, the input is higher, the output will be higher. And the average educational level of the parents is another input. So we would expect that if on average the higher education, the parents have higher education, that means that the students should score better. So basically we want to see, is it true that we want to test, like for example one of the school have higher inputs, so is it actually also producing higher outputs compared to other schools? So in this one we are actually testing on the efficiency, and we can use the data envelopment analysis example. This is very very interesting, in which some of you may want to do this in your FYP. Yeah. Alright, so now let's look at this. We want to compare between the inputs and the outputs. So the inputs we have, number one is the teacher to student ratio, and number two is supplementary funds per student, and the third is the average educational level of the parents. So the higher the three inputs, we would expect the higher the three outputs here. So the output is the reading, math, and history scores. Now let's look at this one between the four schools here. So input number one, which is teacher to student ratio, we can see that Carey having the highest teacher to student ratio, and then in terms of the supplementary funds, we can see that Delancey has the highest. Right, and okay. And in terms of number three, which is input number three, the average educational level of parents, I believe this is like probably years of schooling. We can see that Delancey has the highest. Yeah, Delancey has the highest one. I'm trying to get my my head around this one. Like, okay, let me see if one or two or three. Okay, all right. And this is the output, where this is the probably the average score of reading, mathematics and history. So we would expect that Delancey, having some of the highest inputs, would also have the highest output. So how do we want to test this? Yeah. So in terms of representing the DEA problem in linear programming, it is a little bit different, but more or less it's still under linear programming methods. So we have xi, which is a price per unit of each output. We call it a price. Yeah, a price per unit for each output, and y is for the input. And we can summarize the model in terms of this one. So the objective is to maximize the value of, let's say, yeah, for if you want to do DEA, you really have to choose which units that you want to focus on. Like for example, here we are interested in looking at Delancey. So once we choose Delancey, then we want to compare Delancey with all the other schools, and we want to see whether Delancey is an efficient school or not. And because we use Delancey, so the objective function is maximizing the value of Delancey's output. So this is the test scores of students from Delancey school: 81, 73 and 69, which is the scores for the math, history and reading from Delancey: 81, 73 and 69. So we put it like this, and then subject to the first constraint is actually the input for Delancey. Okay, so you can see 0.06, 460 and 13.1. So all these inputs we equate to 1. This is because we want to scale the Delancey school inputs to 1. So if it is equal to 1, then it is called as efficient. Now, to say something is efficient, so I just put there F. Yeah, to say something is efficient, we would have the ratio of the output to the ratio of the input. Okay, so if it is like 100% efficient, it can go to 100%, or we just put 1. Okay, but we wouldn't expect that it will be more than 1. So that's why we have like the ratio of output per input must be less than or equal to 1. It could be 1, but the maximum that it can go is 1. And for this one, the output is basically, we just put all the constraint in terms of the output is less than or equal to the inputs. So that's what we do for all the 4 constraints here. So including the Delanceys, yeah, you can see the last one is the Delanceys. So we just put all the school's input is less than all the school's output less than all the school inputs, and then we follow suits for the second school, the third school, and also Delancey itself. Yeah, so in total we have 5 constraints. Okay, now let's try to solve this using Microsoft Excel. Okay, in Microsoft Excel, I've already put all the inputs and all the outputs. So this is all the outputs for all the 4 schools, and this is all the inputs for all the 4 schools. Yeah, and each of this is actually each of this output price multiply with the outputs of the first school, and this is the output price multiply with the second school, and so on. And for the value of inputs, so this is the each of the inputs for each of the school multiply with the input prices. Okay, now, and finally is the efficiency. So efficiency is, because we are particularly looking at Delancey, so the efficiency for Delancey is given by the outputs of Delancey and multiply with the output prices, and we want to see whether it is equal to 1 or it is less than 1. Okay, so now let's try to solve this problem. And we put setting the objective as C16. Okay, and this is by changing the variables from B12, changing the variables of this one, as well as, I just put there comma, as well as the column D, and then we set the objective, the constraint. Well, the first one is the value of input for Delancey is equal to 1 if you look at the very first constraint of that you can see from the slides, yeah. And then I just add, and then the next one is all the value of outputs must be less than or equal to all the value of inputs. So this is referring to all the other. Okay, G5. Oh, sorry, I made a mistake. This one is supposed to be H, and on the right hand side is supposed to be J. Right. Okay. The maximum number that you can get from the efficiency is 1. If the value that you get is 1, that means that Delancey is efficient. Delancey is an efficient school compared to all the other schools, yeah, because we believe that Delancey having a higher prices or a higher amount of the inputs, so we would expect that the outputs will also be higher. But if we look at this analysis, we look at this figure, we would say that comparing to other schools who have lesser inputs than Delancey, but they are doing better. So that's why the efficiency score for Delancey is 0.8. You can do the same, you can repeat the same for each of the schools, yeah, and then you can see whether the other schools are more efficient than Delancey. So previously, I think last year, I came across a PhD student doing this analysis, and he is actually collecting real data, of course, on universities in Malaysia. It's very interesting findings. And he looked at the efficiency of universities in terms of the input and output, and he made recommendations. It's very interesting. So if any one of you wants to do this, you're, feel free to explore. And I think that's all for the modeling examples.